Let's begin. Hello, my name is Mr. Ryu.
Say that again?
Mr. Ryu.
Ryu.
Yeah. And then today my lecture is about the chain rule. And then compared to other lectures, because chain rule is what we've done in our calculus BC course, if you remember the materials. So my class will be not that hard, not very long, so you guys can just relax and enjoy and follow with me. So before I start, I want to talk about history of calculus. So, because we are all geniuses. You guys, Isaac Newton and Leibniz developed calculus in their two different ways. And for the chain rule, we're gonna use the Leibniz notation so that we can do calculations with the derivatives. So keep that in mind. Let's jump into the chapter. So the first thing is composition of functions. Can anybody recall something from a calculus class and tell me what composite function is?
F of g of x.
You did that in pre-calculus as well, too.
Oh, yeah. Well, some did not take pre-calculus, so. The composite function is something like f of g of x.
That's composition of functions.
Composition of function. Composite function is something like this.
Yeah.
So, but this is for single variable, right? Now we're learning multivariable calculus. So for this composite function, we usually write function f as f of x, right? However, we can see that this variable of f, which is x, is now substituted as g of x, so that f's variable is now a function.
Yeah.
So as now we're learning multivariable, right? We can expand this to multivariable scope. So let's just make a function of for this a single variable. For multivariable, let's say you have f of x of n y. Now what can we do to make composite functions? We can substitute x and y into different functions. And the thing is that these two different functions can have different variables other than x and y. So let's make it two another variables, u and v. And let's say that x is x is h of u and v, and y will be g of u and v. Then f becomes f of h of u and v and g of u and v. So this is how composite function in multivariable will look like. So let's look at example 1 on page 815. So this shows, and this needs the concept of local linearity and differentials that we learned from data class. If you look at example 1, do not read the question thoroughly, just look at the solution, and you can see the differential. Delta C is approximately FR delta R plus FT delta T. And then from the question, we can know that FR is 3.3 and FT is -5. So we can specify this equation. And from the question, it says that rainfall is decreasing at 0.2 centimeter per year and temperature is increasing 0.1 per year. And we have to change dc dt. So we have to solve dc dt. But the thing is that we don't see t here. T is not a variable given in this equation. So we have to solve the delta c for t. And then from the question, we see that setting t as here, you can see that delta r dr dt is negative 0.2 and d big T and d big T d small t is 0.1.
That's
we-
given in the problem, right?
Yeah, it's given the problem. So what is it? 0.1. And then we can remember what I said about Leibniz notation of calculus and derivative. We said we can do simple calculations with it. So we can multiply dt to both sides, which gives us dr equals negative 0.2 dt, and d large t equals 0.1 times dt. So by this we can get this and this, right? So delta r will be approximately similar to dr, which is negative 0.2 dt, and delta t will be similar to dt, which is 0.1 dt. Now we have these, we can solve delta c in terms of dt, right? So we can plug these in, and the answer, you'll have the answer. Okay. Should I go here or just erase? Is everybody fine?
Yeah.
Okay. Okay. And now let's play with 3 variables. Let's see that z is f x y, and x is a complex function in terms of in t. So let's say x is g of t, y is h of t. By using these, so this will make function z as a complex function of t, which makes f of g of t and h of t. A, B, C, D, E, F, G, H, I, G, H, okay. That's your word. So, and this is z. Now we want to solve dz and dt. So we have to derive this. So, as you remember from single calculus, if we want to derive a complex function, we first solve the derivative of the complex function, and then we multiply the function inside.
Yes.
Derivative of the function inside. So calling look like we're gonna do a similar thing here, but I think it's like we can't like instinctively see how it's gonna be like in multivariable, right? So we can use the concept of local linearity to derive the formula for a derivation of complex function multivariable. So looking back to example number 1, we again want to go back to differentials, which says that delta f is delta fx delta x plus delta fy delta y. And then because we know these, we can solve dx dt and dy dt, right? By doing this, we can say that dx dt times delta t is approximately delta x, and dy dt times delta t is approximately delta y. Is everybody with me up to this point? Okay, so keeping this concept of differential in mind, we can use this. I'll just change it to z. So delta z will be fx dx dt times delta t plus fy dy dt times delta t. And now let's see what we can do with the fx and fy. We can do partial derivatives. We can represent these as partial derivatives. So we can change the notation simply. Delta z will be
Oh.
Mm-hmm. So if in this case we can simplify this as right, and then given that, well, delta t will not be 0 because it's change. And then we can send t to infinity. No, t to 0. Yes, we can send t to 0, which will give to make this not delta but d. So will give us and this will be the derivative of this function. Yay.
I have a question back over there. So over there you said that dx over dt times delta t is approximately delta x, right? So then that means delta z is approximately.
Oh yeah,
No, that's yeah,
different dose.
for close enough, yeah. And then only then, once we get to the limit, can we say it's actually equal. Okay. Okay.
I just was not considered
Yeah.
to be notation here.
Okay. Great.
Is everybody fine with this? With the result?
If d is equal to the theta looking thing, what do you call it again?
D in this?
Yes, they're interchangeable.
No, this is for partial derivative, and this is for single variable derivative.
Oh.
So yeah,
Okay.
so in single calculus we did to get to this and get dx dy. But in this case, this is partial derivative and this is single variable derivative, so we can't cancel these out.
Okay, got it.
So can I erase these? Okay. Now this was a algebraic proof or to derive a formula. What I'm going to do now is I'm going to show you guys a tip to solve this using diagrams. At first I didn't get it when I first saw this. After understanding the mechanism, it was much easier, and it will be better when we will deal with much more variables. So let's go back to this. We can see 4 variables here, right? Z, Z, X, Y, and T, right? So we write Z, X, Y, and T. Let's see the relationship here. If you go from z to x, it is right. And if you go x to t, it is same here. If you go from z to y, it's, and if you go from y to z, we get,
From Z to T, it's triangle.
yes. And what we want to solve is dz and dt, so we connect these. If we connect these, we go like this and this way, right? So, and we multiply things in the way. So, dz dt will look like this times this, which is dz dx times dx dt plus multiply the product of this and this, which is dz dy times dy dt. So by using this, we can deal with complex functions with more variables. So, before that, let's do an example. Page 816, example 2. Let's solve that. Okay, we have z equals f of x comma y, and x comma y is x sine y,
X is T squared.
and x is t squared,
Y is
and y is 2t plus 1. And we have to compute gt, right? So, let's recall
where Z is GT.
where z is gt, and z is gt. So we have to solve g delta t, the g prime t. Okay, so what we do, we just do what we did.
Profound.
Yeah. So dz dt is and what is the partial derivative of this function in terms of x?
Sine Y.
Yes.
Sine Y.
And dx dt will be 2t, right?
T.
And then partial derivative of z in terms of y is,
X cosine.
and then dy dt will be
2.
2. So
Wow.
now we have
Yeah.
the answer.
3 variables. To represent. Why?
No, I'm gonna erase the example. And then here, let's do something with 3 variables. So look at this. Originally, what we just did is this, right? Now we're gonna change this. Change this into u and v. U and v. So, complex function will look like. So it's like a multivariable function, complex of multivariable function. So how are we gonna do this? Are we gonna do like the thing that we did, like the algebraic proof? No. Remember this. We're gonna make a diagram to see the relationship. So what do we have? We have v, x, y, u, v for each. No, uv. Yeah, they repeat. So what do we do? Relationship from z to x will be
Partial z with respect.
partial of z over partial x. Relationship between x and y, x and u will be
Lower partial u.
Yeah.
No, that's like the theta looking one at the.
Oh.
Like,
Yeah.
Hey, by the way, what's this called again?
Delta.
Delta.
I don't call it
Thank
delta. That's a lowercase delta.
you.
Yeah.
low delta. What is the relationship here?
Partial z, partial y.
And this is partial y, partial v, and that's not it. We can draw more
From
lines
X to
from
V.
x to v. It is
Oh.
No, it's delta.
a delta.
Oh, yeah, that's. Okay, there's different. I see.
Okay. Now we have this. We do the same thing. If we want to solve dz du, we can start from u and go to z by multiplying everything in its way. So let's do dz d the delta z delta u will be multiplying everything here. Where's the green pen? So we go like this and this. So we multiply these, and these. It'll be d delta z delta x times delta x delta u plus what's in this part? Delta z delta y times delta y and delta u. We do the same thing for v and z. V and z will instead. If you were v and z, we go this way and this way. So we multiply things in that way. The delta z delta v will look like this multiply this, which is delta z delta x times delta x delta v plus what's in this part, which is delta z delta y times delta y and delta v. So if we have more variables, we can draw this kind of relationship and see how the derivative is constructed, how they build up in order to solve the partial derivative of composite functions with more than one variables. So we can do example 4. This looks very hard, looks very dirty, right?
Yeah.
Like, your first impression must be like, I'm not gonna solve this. Well, even though you don't want to, we have to, so I'm gonna do it anyways. So let's see. W is what? X squared e to y, and x is for you, and y is 3u squared 2v minus 2v. I have to compute dw du and dw dv. However, I'm going to do only one. You guys can choose which one to do. Tell me what you want to do.
The second
The
one.
second one?
Because I see a 0 in the middle.
Oh, nice insight there. So we're going to solve dw dv. Now, let's reconstruct the diagram. We have w here, x, y. I'm going to make it bigger. We have w here, x, y, and u and v. Let's do this. What is dw dx?
Delta w delta x.
Yes, what is that?
I'm confused. Where is? Oh, that's a v. Okay,
Oh,
never mind. Okay, all right.
sorry for my handwriting.
Mm-hmm.
What is dw dx?
2x e to the y.
Mm-hmm. For clarity's sake, we just do this. No, that looks like power. And what is dx du?
4.
4.
Are we doing dw dv?
Yes. We're just like drawing the diagram.
Just completing the diagram
Oh,
before we
okay.
complete.
What is dw dy?
W dy
X.
x
Same
squared.
thing.
Yeah. And what is dy dt?
Minus 2.
Oh yeah, minus 2.
And what is dx dv?
0.
0. And what is dy du?
6y.
6y.
6u.
So we have to solve dw dv, right? So we get this and this, and we multiply this way. Yes. So that gives us yes, that gives us 0 delta w delta v equals 2 dy x times 0 plus 6 minus 2 times x squared e y, which is negative 2x squared e y. Okay, so this is like really it. Like the application to physical chemistry. I like chemistry, so I'm gonna just skip this part, and I'm gonna assign you guys homework. Go to page 822. 16, 17, 20, 21.
I'll do 17.
Jalen takes 17, 20, 21.
I'll do 17.
I'll
do 16 though.
Okay.
Oh.
And G1?
I'll go.
20?
Yeah.
20?
Thank you.
And that makes Mrs. Isle number 21.
Oh, okay. Y'all keep assigning me problems that I keep forgetting to do.
And then, like, I have an interesting problem.
Well, I have a question. Looking at your notes, you forgot a vocabulary, the Liebritz notation.
Leibniz notation, that's what I just told, that's what I mentioned in the beginning. So, dx.
I didn't hear that Liebritz, so
Didn't I mention?
Yeah, you mentioned.
okay.
Yeah, I did.
Thank you. All right.
It's okay.
Mhm.